Hi, I'm Detective Incognito, and I explore events that challenge what we know about our current world. What you're about to hear will change the way you see life. Welcome to another investigation. Osaka University, 2023. Scientists place a person inside an fMRI scanner and show them photographs. Hours later, artificial intelligence generates new images depicting exactly what that person saw. Not by accessing the photographs, not by analyzing camera feeds, by reading patterns of brain activity alone. No cameras captured these scenes, no external input whatsoever. The AI reconstructed visual experiences from neural signals. Translating thought into image, researchers call this brain decoding, the translation of mental activity into external representations. If you want to understand how machines can visualize what humans perceive by reading only brain patterns, subscribe to this channel, because what scientists achieved challenges everything we thought possible about the privacy of consciousness itself. This is the story of images created from zero input, except the electrical whispers of neurons firing in darkness. In December 2022 and March 2023, Takagi and Shinji Nishimoto at Osaka University published research that would redefine the boundaries between mind and machine. Using functional magnetic resonance imaging, they recorded neural activity while for subjects viewed 10,000 different images. The dataset contained diverse photographs, landscapes, animals, everyday objects, human faces. Each image produced a unique pattern of activation across visual cortex regions. The innovation was combining these fMRI patterns with stable diffusion and a specially designed semantic decoder. The system didn't just capture vague outlines, it produced reconstructions with remarkable fidelity, preserving both the semantic content of what subjects saw and the structural layout of scenes. When a person viewed a clock tower, the reconstruction showed a clock tower. When they saw a bear, the output depicted a bear. The correspondence wasn't perfect, but it was unmistakably accurate. But the journey to this breakthrough took decades. The quest to visualize thought has occupied neuroscientists since brain imaging technology became sufficiently advanced. Early attempts by Miyawaki in 2008 produced rudimentary reconstructions, crude approximations that captured little more than basic shapes. The field progressed slowly. Research teams led by Shen Horikawa, Majima, and Kamitani published deep image reconstruction in 2019, achieving better results but facing fundamental limitations. Their systems could reconstruct either the layout of a scene or its semantic content, but struggled to capture both simultaneously. Images lacked fine details. Colors appeared muted. Objects remained abstract. The challenge was profound. Brain activity produces incredibly noisy data compared to digital images. An fMRI voxel represents activity across millions of neurons, averaging their signals into a single measurement. Brain Diffuser emerged in 2023. Introducing a two-stage framework combining variational autoencoders with latent diffusion models. MinDiffuser followed in March 2023, leveraging vector quantized autoencoders and clip text embeddings. MindEye, published in October 2023, achieved 93.2% accuracy, identifying the exact image a subject had viewed from among thousands of candidates. The progression was clear. Early systems generated abstract forms. Modern approaches produce recognizable photographs. Researchers suggest this reveals profound truths about perception. The technical process operates in stages that mirror how the brain itself processes visual information. In the first stage, a decoder network translates fMRI patterns into latent representations compatible with stable diffusion. Simultaneously, another component generates clip embeddings, mathematical descriptions that capture semantic meaning. Stable diffusion uses these inputs to generate a preliminary reconstruction. Transforming noise into coherent visuals, the second stage refines this output. Low-level visual features adjust structural details through backpropagation. This mimics how the brain processes vision across multiple stages, from detecting edges and colors to recognizing objects and scenes, the correspondence between artificial and biological vision hierarchies isn't coincidental. Deep neural networks were originally inspired by neuroscience research. This creates a reciprocal relationship. AI systems help decode brain activity precisely because they process information similarly. When reconstructing a clock tower, early models produced abstract shapes. Adding semantic captions enabled precise reconstruction of architectural details. The system works through statistical correlation. Patterns consistently associated with specific objects become signatures the AI learns to recognize. Current limitations remain significant. The process requires 30 to 40 hours of scanning per subject. Studies indicate the implications extend far beyond neuroscience. The technology promises transformative applications across medicine, law, and human communication. Patients with major depressive disorder sometimes exhibit altered visual perception. Brain decoding might reveal how depression distorts their experiential world, with reconstructions emphasizing emotionally negative aspects. Communication with locked-in syndrome patients, conscious but unable to move or speak, could become possible if they can see and form mental images. Decoding might provide a visual channel for expressing thoughts. Forensic applications raise both promise and profound concern. Imagine a witness to a crime unable to articulate what they saw. Brain imaging could potentially reconstruct the scene from memory. Or imagine a suspect questioned about their whereabouts. A reconstructed image shows them at the crime scene. The ethical complexities are staggering. Research extends beyond passively viewed images to mental imagery. Shen's 2019 paper demonstrated reconstruction of imagined scenes, not just perceived ones. Radboud University researchers reconstructed faces with accuracy matching the originals. The debate intensifies around mental privacy. If thoughts can be visualized without consent, what protections exist for consciousness itself? Can such evidence be admissible in court? What safeguards prevent misuse? This remains one of neuroscience's most profound questions. The technology stands at a threshold between laboratory demonstration and practical application. Current systems require massive, expensive MRI machines. Real-time reconstruction, without hours of preparation, remains an elusive goal. Researchers have begun addressing video reconstruction. Wang and colleagues in 2020 published methods for reconstructing natural videos from fMRI data, capturing not just static images but motion and temporal dynamics. The next frontier many scientists envision is dream decoding. If waking perception can be visualized, why not the elaborate imagery of sleep? Fundamental limitations complicate this vision. fMRI resolution remains coarse compared to the brain's actual information processing. Consumer applications seem distant. MRI machines cost millions of dollars and cannot leave clinical settings. Future miniaturization might employ EEG-based systems. These provide lower spatial resolution but offer portability. The philosophical question grows more urgent. If thoughts become externally visible, can they remain private? Does the mere possibility of visualization change the nature of inner experience? Scientists still debate the boundary between observation and invasion. Brain decoding doesn't literally read minds in the sense of accessing subjective experience. It translates patterns of neural activity into visual representations. Based on statistical relationships, the distinction matters. What the AI produces isn't precisely what someone experienced but an approximation, a best guess constrained by limited information. The discovery reveals something profound about perception itself. We don't passively record reality like cameras. Our brains construct experience from fragmentary sensory input, filling gaps, imposing structure. The reconstructed images reflect this constructed nature. They capture not raw sensation, but processed interpretation. The question scientists continue investigating isn't whether perfect reconstruction is possible. Current evidence suggests fundamental barriers exist. The question is how much can be revealed, and whether those revelations respect or violate the sanctuary of private thought. Yuta Kagi and Shinji Nishimoto emphasize that their method reveals how the brain represents the world, providing windows into neural processing that were previously inaccessible. As these windows grow clearer, society must grapple with implications that extend far beyond technical achievement into ethics, privacy, and the nature of consciousness. If AI can see what you see, visualize what you imagine, reconstruct what you remember, what does that mean for the privacy of thought? The technology exists now. The questions it raises have only begun to be asked. Understanding brain decoding isn't about fear, but about informed engagement with capabilities that will shape medicine, law, and human rights. If exploring the frontiers between mind and machine fascinates you, join this journey, because studying how AI translates thought into image teaches us about the surprising nature of consciousness, the constructed quality of perception, and the delicate boundary between what we think and what can be known about our thinking. If you liked, subscribe to the channel, like the video, and activate the bell. Leave your opinion in the comments to let me know what you thought. Thanks for sticking around, and see you in the next video.